Okay. So thank you very much, and good morning. Well, good afternoon in China. Deep afternoon. So thanks a lot for organizers, first of all, for inviting me and giving me opportunity to present talk here. I will just change gears a little bit. I'm not sure I'm very much enthusiastic to prepare so many slides. I don't know how to do it, so I will try, let's say, classic style. Okay. And also you told that my title of my talk is Infinite Derivative Gravities. I remember I sent you somewhat different, but anyway. So I will be talking about resolution of singularities, okay? I will be talking about resolving singularities, okay? This is actually infinite derivative gravity, okay? Infinite derivative gravity. This is what I would like to speak about. I have 1 hour, yeah? Okay, thank you. Okay, 1 hour, yeah? If I can add up 50 plus 10, it's 60, yeah? Okay, good. Okay. Before I will go to resolution of singularities, which is my primary interest recently, I would like to speak a little bit about what is infinite derivative theories, what is infinite derivative gravity, and because gravity itself is already a complicated subject, we already had yesterday fascinating discussion. I will start with theory, okay? So about infinite derivative theory, here is this left part of the board, it will be about just fields. And I will speak about here on this left side, I will speak about scalar field phi, okay? Scalar field phi is a good thing. And for this, we can write a Lagrangian, and most likely we will write it like this, yeah? And here there is a lot of things to mention, and I will even write an action. Yeah. And here there are a lot of things to mention. First of all, I will try to stick to 4 dimensions, even though I'm not sure that we're living in 4 dimensions, but we observe 4 around. Then I put here minus, and minus means that I have signature like this, and I prefer it just because it's simpler. And because it's minus here, it's not a ghost. And when I say ghost, I mean simply particle with a wrong sign of kinetic term. Okay, and here we can write some interaction. This would be a fascinating Lagrangian for scalar field, but actually inspired by gravity considerations, we know that we want to add higher derivatives in order to make things work. So let's train on scalar field, and on scalar field we know that we cannot add higher derivatives easily. We generate a ghost, okay? In order to generate a ghost, you don't have to think, you don't have to work a lot, you just write something like instead of one D'Alembertian, you write another D'Alembertian, and you already know that you have generated a ghost. Why do you do it? Because your propagator is inverse of this kinetic operator. And on contrary to the previous talk, I will not designate particles like real or virtual. For me, all particles are particles. Okay, whatever I get is mine. I'm not sure I have a rule how to designate them, so that I will not. And whatever I write here, I just simply do inversion of this. And if I do it, I will simply write it like this. And here we clearly see that either A or B should be negative. This is how we say, this is why we say that if there are more than 2 derivatives, there should be something wrong, because we just, from here, we conclude a very simple thing, A plus B should be equal to 0. Yeah, so one of them should be negative. From here, we conclude that there is a ghost. Actually, it's not me who concluded it. It was done by Ostrogradsky in 1850. Yeah. So the starting point for this consideration was made by Ostrogradsky. Let's see. Let me finish at least. Which? This. This. Okay. Do you think it's better? Oh, much better. Okay. So Ostragradsky did it in 1850. It's roughly 170 years ago. However, he didn't speak about infinite number of derivatives. Yeah. Apparently, I want to go to infinite number of derivatives, and again, I'm not the first one who is talking about this. It was a very nice paper by Pace and Uhlenbeck, actually 100 years after Ostrogradsky. It was a brilliant paper by Pace and Uhlenbeck, where they considered infinite derivatives as a possible tool to regularize field theories. It was a very nice paper because they even didn't use language which we use now. There was no words like renormalizability. They were using word divergences and convergence. And actually what they claimed in this paper, they found quite rigorously that if you try to introduce higher derivatives, they tried to introduce higher derivatives here because they tried to write something like this. Yeah. This is what they tried to write explicitly. They were very brave people already 70 years ago. They did it. And they found out a very important thing that achieving at the same time convergence of integrals, unitarity, and causality is impossible. So we have to give up on something. Most likely we will give up on causality, actually, just because there is a chance to violate it at some micro distance, maybe without harming the rest. And it's not nice to give up on convergence, or how we say now, renormalizability and unitarity, okay? Now, however, we should do this trick carefully. And we do this trick carefully in a sense that we want to say that it's better to write something like this for kinetic part of the propagator. Yeah? If we write like this, where this particular sigma is entire function, this is a brilliant object. Because exponent of entire function it's a function which doesn't have poles, or better to say singularities on the complex plane. So since it is entire, then exponent of it doesn't have zeros. Okay, so exponent of entire function, yet another special entire function which doesn't have zero on a complex plane. Surely because it is entire function, it must have one special point, and the special point would be infinity. So at complex infinity here, when box goes to infinity, at complex infinity we have trouble. We have singularity. Because it's exponent of some entire function, this singularity will, by construction, be essential singularity. Okay? This is more or less clear. However, what is much more interesting is that apparently the same structure may have a very good inspiration, may get very good inspiration from string field theory. And actually, this is why I started to think about this kind of theories, because when I was much younger, I was kind of, well, I had no choice. I chose an advisor who was doing string field theory, so I was doing string field theory. And it was a very nice move, actually. I'm not going to introduce here string field theory. Moreover, many of you are familiar with it, or at least with string theory. So I believe that it's not a surprise to you. Just a simple note is that when you have interaction of three strings, when you compute this stuff in string field theory, you have to actually compute 3 times correlator of this. Yeah. And when you will do this, actually this is the origin when you will compute correlator of these 3 exponents, which are 3 vertex operators of 3 strings which collide at one point. This is where you generate for your space-time fields which describe interaction of a string. This is where you generate something looking like this. Okay? And this is actually your, let's say, potential, which is not exactly potential. Yeah, it is something like interaction term, which we don't know what it is. It's not exactly potential. Yeah, it has dependence on momentum, but that's exactly what string is tell you, and this is actually very intuitively correct because in strings you have to somehow describe the fact that vertex is not anymore a point, it's rather some region, and you have to delocalize your interaction in some way. And this is a clear way to delocalize your interaction. Okay. Then working further, if you go further in strings, and going further in strings means if you include higher and higher mass level mass excitations, you will find out that this function is getting changed somehow as long as you effectively uh, express degrees of freedom. But the point is that whatever you should have here, there should be some so-called form factor. So this I would name form factor. And the thing which we know that we don't know exactly what they are, but they should be some entire functions which do not introduce singularities in the interaction. Then in principle, if you have your kinetic term on top of this, yeah, then essentially by field redefinition like this, if you take this part to be equal some phi, you can move everything to the propagator. So it's your choice. It's not like, I don't say actually propagator here is non-local. I'm saying that you can move this non-locality to propagator as a matter of computational simplicity. Okay. It's not always possible if you have, for example, many fields or something like this, but what it's possible to do it when you have one field configuration. And at least it should be possible to consider this as some model. Okay, so it will be some model sink. Okay, if it is some model sink, then it's good to start with. Okay, so the model essentially is some scalar field which has non-local either propagator or interaction, whatever you choose. Because actually we start in a more global picture with non-local interaction, I don't ask myself questions like, for example, Cullen-Lemon representation of this propagator is local. Okay, and the full propagator, when you will compute it, if you can compute full propagator at some point, it will be anyway. It can be anyway localized because you have to canonically normalize your scalar, your degree of freedom. So I don't think it should be a problem. And always, this kind of stuff should be treated perturbatively. Yeah, this lambda should be treated perturbatively. This essentially corresponds to string coupling constant in this description. Okay. Now, naively, yes, but I say that I would prefer this to be treated perturbatively. Then this is my propagator. It looks perfectly local. Yeah. Okay. Then even if I will compute the full propagator and will account all the loop corrections to this, at the eventual stage, what I expect, whatever I will get, I would prefer to have structure like this. Okay. Because this structure would guarantee me that there is no new state or there is no ghost. Okay. To be fancy, I will put here 2. And at this stage, when I have such kind of propagator, no matter when I got it, I will just do a redefinition and say that this thing is now equal to new field and we'll be happy. Okay. Or at least I hope that I can be happy, because if I will not be happy, then it means the string theory is not unitary. Okay. This is extremely difficult to sell in any community. Okay. Because if I will start talking the string theory is not unitary, first of all, it's the baseless statement. And second, it's too much of exaggeration. Yeah? Now, but for the moment, I want to see what happens with this kind of theory, or at least I want to question a bit simpler maybe question, which is whether this thing can be unitary. Okay, And the first thing, the first nice paper which was written, it was written by Pius and Sen. It was written in 2016. It was explicitly a paper about such a Lagrangian. They were studying, well, actually they were studying Lagrangian like this. But, well, they did not specify any shape of this. They put some function of this, okay? And what they exactly did, they were discussing Katkowski rules in this particular setup. After this, a little bit later, we repeated the same study with Anna Tokareva, who is here. We repeated on a simple example because a paper of Bioshoxian, let's say it's simple words, is complicated, okay? We made it a bit simpler, and what we did, we simply have taken such a Lagrangian, yeah? Instead of this V of phi, we have taken pi to the fourth. And we started with simple operator. Simple operator is sigma of box equal box, yeah? Or let's say alpha box. And from here, we tried to just do computations. And what we did, we computed one loop correction to the vertex. And from this computation, which we managed to do only in the, well, completely managed to do in the case when mass goes to zero, in which case we could do it analytically, we could find that apparently, well, answer is a bit long. Let me take it. I mean, it's a bit longer than I can remember. But apparently what we found that if we do manage to compute this, then we will find that amplitude of this will be something like this. And here it will be this I, and this I can be written like standard contribution which you find in a local case, plus something a little bit which we find in our non-local exercise in the case of this particular exponential form factor, yeah? When we have just exponent of box. The point here is, well, and there are two other terms here, which kind of resemble these two. So the point of this computation was to show two very important things. Thing number one is that there is a clear smooth limit when alpha goes to zero. Because when alpha goes to zero, everything should come to a local theory, and the limit exists. Another most important thing was to show that optical theorem is explicitly satisfied, and it is, because actually you have to just pay attention to this contribution, okay? Which is common like in a local case, okay? And all the rest goes away. And this you can track by taking the limit properly. Now, when you do it, you become a bit more happy because now you understand that essential singularity at infinity is not a big deal. Yeah? Even though it exists, it's not a big deal. And apparently what we understood here is, can I put here? Yeah, so what we understood here is the following. What we understood here is the fact that we did computation in Euclidean, and then did analytic continuation to Lorentzian. Which is essentially, so what we did all computations in Euclidean signature and analytically continued the results to Lorentzian signature, which is essentially equivalent to a very complicated story advertised by Shoxian, which was telling us that instead of doing weak rotation and closing contour like this, which you cannot anyway because of essential singularity, you have to do some contour modification and do things like modifying contour this way, encircling all the possible poles which you can encounter here. Yeah. It is not obvious, but apparently these two approaches, like analytic continuation and contour modifications, they give the same result, okay? And most likely it should be true in any other setting. With this in mind, and having the fact that we are quite familiar now with infinite derivative construction, at least in scalar field, I'm moving to gravity, because my intention is to convince you that in gravity we need infinite number of derivatives. Okay, why do I want infinite number of derivatives in in gravity? In gravity, I want infinite number of derivatives because I failed, or at least all the literature failed to write gravity action with finite number of derivatives without problems. Okay, so from this perspective, what I do, I'm now trying to go in some other way, and instead of writing just action, which would be like this, which is just Einstein, and which is not yet stellar action, just because stellar action is not enough, yeah? For me, it's not enough just because, yeah, W is a Weyl tensor, yeah? This thing is definitely not enough for me just because it produces a ghost, okay? And as I started with, I want to treat all particles have their own right to be treated independently and as the same token. Everything which gives you a pole is a particle, okay? So everything what gives you a pole in the propagator is a particle. This is what I try to, this is from where I try to go. So, and in this theory, which was written in 1977, yeah, by Stella, uh, we have a perfectly renormalizable gravity without unitarity. And now, being inspired by this left-hand side, and being inspired by this Lagrangian, which is with infinite derivative, I'm asking a question whether I can put infinite derivative in my gravity action and be happy. Because what I need higher derivatives, okay? But I learned from here that I can, in principle, put them in infinite number. And now I'm trying to ask a question whether I can put them in gravity action in infinite number. And what I do, even without all the, and my problem is that I cannot use string motivation because I don't know how to obtain the same result from closed string field theory. For example, because nobody knows what is closed string field theory. And still there are debates how to construct at least something which looks like a closed string field theory. Okay. And yeah.
Take up with the question that's being asked. So you're asking, can I consistently construct an infinite derivative expansion for the Einstein-Hilbert action? But regardless of this whole debate whether string theory is true or not, we know, I mean, we have the examples, it's there, there's an infinite derivative expansion very explicitly, so it's just that we have a hard time computing all of the coefficients.
Yeah.
Understand what the conceptual question?
No, there is no conceptual question yet. The conceptual question which will come next. There is no still conceptual question, okay? Because I know I took part in constructing one of these sections, so I hope it exists, yeah? And I just want to write it down, okay? I want just to explain it to people who may not be familiar. Since you look like familiar, then for you it's very easy, okay? But it may be not like for everyone easy, the simple motivation how to arrive to infinite derivative action, okay? And motivation for this was very actually simple. Motivation was like this. We didn't, instead of just writing whatever trill and tries here, we started somewhat other way around. Another way around was to write all possible terms which can be in principle written based on Riemann curvature. Okay? So if you start with the Riemann tensor, and if you don't complicate your life with, for example, torsion or metric incompatibility, which is difficult, I accept it's very difficult. If you go a simple way and consider a metric compatible connection, then and d is the covariant derivative here, then in principle, question is the following. If you write any possible term which you can write out of Riemann tensor and covariant derivative, can you single out the set of terms which will contribute to propagator, at least around Minkowski? Actually, we did it not around Minkowski, but around maximal symmetric spacetime. And the answer was that we have to modify this a little bit. And modification a little bit, which we found out, it should look like this. So in principle, this is the action which if you want, contains cosmological constant and contains terms like this. And these two, F and FW, are nothing but some Taylor series. We understand them as Taylor series around zero. Okay. So they are functions analytic at zero. Why we want analytic at zero? Because we want Newtonian limit. Why we write cosmological constant? Simply because we, in principle, can write it. If cosmological constant is there, then background will be de Sitter or anti-de Sitter. If cosmological constant is not here, background will be Minkowski. And the claim, yes, these Fn are constants. And the claim is that this is everything what you can write in order to write what will contribute to a propagator. And if you write anything else, it will either not contribute to propagator or will give a trivial contribution. Oh, sorry, either will not contribute or can give a equivalent contribution to something written here. Okay, equivalent, it means that simply will amount to redefinition of these Fn coefficients. Okay. Now, if you work a little bit harder, but not too much harder, you will find out that, well, you can ask me why, for example, I don't write something like R mu, some function of the Lambertian R mu, where R mu is Ricci tensor. And answer is very simple. I don't write it because it can be excluded by equations by Bianchi identities. Okay. Another thing which is less trivial, that in principle there is a magic contribution, there is a magic combination which arises, which looks like this. In the denominator of operator which contributes to scalar degree of freedom propagator. So essentially the question is that this imposes a constraint, and these two form factors should be either given total zero or be equivalent to some entire function. This comes simply from resolution of singularity, resolution of constraints. Resolution of constraints. It is analogous to the situation when you make use of the Gauss law in electrodynamics to reduce degrees of freedom. Because you remember, in electrodynamics, you have a mu. It looks like a vector. It has 4 degrees of freedom. Then you gauge 1 away, but you still have to come to 2. Yes? And you have to work a little bit harder. And you use Gauss law and you eliminate 1. And you are left with 2. The same is here. The same is here. There are constraint equations in the system of Einstein equations. And when you resolve constraints, you understand that these two form factors are not independent. Practically speaking, it does not simplify your life a lot, but it is a good piece of knowledge, let's say, that we now kind of narrowed our formulation of a model up to one form factor. Then you can obtain, you can vary this with respect to transverse and traceless perturbation. When I say vary this, I mean that you perturb metric like, for simplicity around Minkowski, you will write like this. And then you will write for transverse and traceless part of H mu, you will find that propagator of it is, which is transverse and traceless, is looking like this. And now your task is to try to connect this part with that part. And to connect it, it means that this already produce you a trivial pole. This factor produce you a trivial pole, and this creates you graviton, yeah? The question is that since you don't want anything beyond graviton, and you don't want new particles, and moreover, you know, if you will have new particles, they will be ghosts. What you want to say that this combination, which is written here, should be exponent of entire function. Okay, this is what you want to say. And this is how this can be constructed and how you can create something without a ghost. Okay, and now clearly we understand that in stellar case, stellar essentially means Fw equal 1. In case of Fw equal 1, you clearly create here a second pole. Okay, so from this perspective, it's clear. There are two things are clear here. First thing, which is clear, that you can have a model without a ghost if you have such a identification. And this function, which you don't know, but which you put here, okay? And your primary wish is to find out what is function. But another thing is that it looks like from here, pure algebraically, that you don't have anything in between. You cannot easily create any model which will have a finite number of derivatives and simultaneously no ghosts. Okay. So since on the left side of this board, I kind of tried to convince you that infinite derivatives is not a big deal, and we can work with them and live with them and have unitary models. There is a hope that we'll have the same here, okay? Now, because now we thinking about this Lagrangian like a Lagrangian giving something unitary and renormalizable. I don't discuss here renormalizability, but I get it nearly as granted, okay? Why I do this? Because it looks like obvious that having such a freedom of choosing this factor, I can make all loop contributions suppressed. Okay. If I will have anything divergent, and I will have, it will be one loop correction to the graviton propagator. It will be local. It will be divergent anyway, because whatever you have here, like suppression factor in the propagator, it will be the same factor in the vertex. So in principle, they will cancel out. One loop means the same number of internal lines and vertices. It means that they will cancel out in one loop explicitly. This one should be renormalized, but we know how to do it. Stella already did it. Counter terms will be local, just because there will be no non-local contribution here, and it looks like we are done with this, and all the rest, like two loops and higher, can be renormalized by power counting. And there we also having diffeomorphism invariance because we didn't break it. Yeah, we have the Slavnov-Taylor identities in place, so it looks like everything is fine. Yeah.
Because they depend on different momenta. So e to the 2 omega and e to the minus 2 omega 2. They don't really simplify because they have different combinations of momenta.
Yes, you are right. But when they have the most singular contribution will come from the fact when these factors will cancel each other, okay? And the rest, when these factors don't cancel each other, will be even better, okay? This just can be, well, in principle, I can just write it down. It just will take me extra 5 minutes. So I don't say you that it will be explicitly very easy and like nothing to do. You have to work out a little bit. e to the box will not be okay for many reasons, and because I would suppose to talk about more singularities, I didn't go into details why exponent of box is good or not. Exponent of box, if you ask this particular question, is not good a function here anyway. Exponent, because what should be here, it should be here a function which first of all is this form factor which is here. As we can learn at least from scalar field example, it should be function which is even function of the Lambertian first, and box is not an even function. And second, it should be a function which produce you think, and think like this stuff when z goes to infinity behaves like z to the power p along positive real line, okay, where p is some power, okay? This you can arrange. There are explicit examples. I was not thinking to discuss this, but since you're asking, it's a good point. The explicit example of this can be like omega looking like incomplete gamma function of some polynomial of z, okay? Minus gamma minus logarithm of the same polynomial of z. If you write like this, this subtraction of logarithm exactly cancels logarithm contribution in incomplete gamma function. Gamma explicitly cancel constant contribution here, and you restore normalization, which you need for canonical normalization. What is left after this is some entire function such that exponent of it behaves as a power law for the positive real line. I don't say it's a unique example, it's a one-off examples, okay? Because the only thing which constrain you entire function is, well, it's not like only, but one of the most powerful things which we know is a famous Liouville theorem, which tells you that the entire function must have singularity. And another story is that in the vicinity of singularity, entire function must have any possible values. And as such, when entire function approaches singularity, it should take, depending on the contour on the complex plane, if it is a singular point, depending on the way how you approach it, you reach any possible value, okay? So in principle, there is no hope, like, for example, organize a weak rotation, but there is a hope at least to organize good behavior along real line. If you have a good behavior along real line, like a power law, then you can, yes, here this p is nothing but degree of this polynomial p capital, okay? If you can realize such a power law example, you can speak about power counting, because otherwise you will not have power counting, because power will be essentially infinite for exponent. And for exponent, you will enter here, and you can track it in this scalar field example, you will enter the strong coupling regime. This is what you don't want, or at least we would be happy to avoid it, okay? Maybe it's the case, but at first we search for possibility to avoid it, okay? Now, so from this point of view, this particular Lagrangian can be considered as renormalizable and unitary. I don't say that renormalizability was worked out explicitly by anyone, but there are a lot of things like power counting, locality of counter term, and presence of diffeomorphism and variance, which guarantees Slavnov-Taylor identities, yeah, which is in favor of the claim. Yeah. Now, neither I say that this particular Lagrangian is end of the story. There are some dots here, which in principle can correspond to something beyond this, okay? I don't know what it is. Neither I'm sure it's important, okay? This Lagrangian is already complicated. Even with constant Fn, it's already complicated, can give you a lot. In particular, it can give you easily embedding of Stravinsky inflation, okay? So in principle, if you want to describe universe, already you can start with, okay? And describe inflation here. And this was matter of several papers which were written with Ravan and with Alexey Stravinsky and with Anna regarding this particular model and several consequences for inflation, okay? However, the question which I started my title with was the resolution of singularities. Okay, so here there is a question: what happens to singularities, which we used to have in gravity, especially in GR, in such a framework? Because in such a framework, you see what I'm saying. I'm saying that I modify my action. By the way, I introduce a scale, yeah, because it's not box, of course. Here it's box divided by some mass. Okay, there is some scale here. Implicitly, there is some scale. I don't know what it is. I just know that it should be somewhere higher than the scale of inflation. Yeah. So if there is some mass of scalaron, which drives inflation or inflaton, whatever you like to name it, it should be something like here, and it should be somewhere here. Here it should be Planck mass. Yeah. So somewhere here it should be squeezed. Here I don't know, is it less or much less than Planck mass? The only thing which I know is that this new mass scale should be much higher than inflation scale, because we don't need this for inflation. Okay, we simply don't need this contribution for inflation. It already works without it. So we're somewhere here. We don't know what the scale is. It's an interesting question. And as I say, this section is already kind of complicated, yeah? Kind of complicated. Just one thing, actually, before I will switch to singularities and black holes, one thing which is a bit strange to me, I don't know a good answer for this. Even if some of you know an answer for this, I would be happy to learn it. In principle, if I go to higher dimensions, I have to include here some constant contribution like this. This should be included, but this is not what I want to ask. This is a matter of computation. What is much more intriguing to me is the fact that if I will carefully write this non-local contribution like this, with coefficients which explicitly remind you nothing but Gauss-Bonnet invariant, with explicitly 1 minus 4 and 1 here, then there is an interesting observation which we did, and which I cannot say I can explain, and I would be happy to know if someone knows geometry very well. Why this particular contribution in four dimensions? Would it be f equal constant? It's the Gauss-Bonnet invariant. Yeah, we should neglect it. On a trivial topology, it should give 0. Yeah. What is interesting? It's interesting that this contribution gives 0. This combination gives 0 contribution to propagator, no matter what is f of box. I can write it as much as I want. It gives 0 contribution to propagator because it explicitly cancel each other. Why this I don't know, but it's just interesting observation, which may be useful for construction of something more general. Okay. A second variation of this is identically 0 in 4 dimensions. Okay. Now, having all this construction and having all these puzzles and nice observations, we go further and we ask a question whether this particular model can be joined somehow with something what we know, or at least what we pretend to know, like black holes. Okay, because many people.
The case, I mean, there is some ambiguity in the fixing the sigma, right?
Yeah. Okay.
But are there some examples, like simple examples, that are consistent to where it is known, like how many relevant directions you have, and how many would they be?
But what do you mean consistent? Consistent.
So essentially, any entire function.
Well, you see, this is actually what we tried to work out with Starobinsky, with Ravan, with Anna. We were trying to plug here inflation and see at least some restrictions from inflationary point of view on this form factor. Okay, as I told, we don't need this modification to drive inflation, but definitely this modification manifests itself in something in inflation, like for example, tensor to scalar ratio. Okay.
That I fix one possible form
Okay.
and say E2 minus box squared that should work, right?
Well, in principle it will not, but anyway, let's see.
But can you say, like, given the one form factors that work, like how many relevant directions you have?
What do you mean relevant directions?
Like the eventuality of the critical manifold. I mean, in like a standard local normalizable quantum field theory, so you can say you can relate the number of relevant directions based on power counting. Here is more difficult, I guess. Yes,
you mean this, but this will be the same as long as you organize this to be power law at infinity. And I gave you an example of power law function like this. This is gamma 0, incomplete gamma function. As long as you fix this, you will be happy to have this some polynomial of z at infinity, and you will have your number of exactly like looking like a local theory at infinity. Okay.
so three parameters.
Free parameters is a good question because it looks like we have this fn to be parameters, but if you go to deep UV regime, where it will be your power law, it will be just your power law decay, and depending, like in any field theory which has power law, you have exactly the same. Okay, if you can manage this, but then there are considerations like about this power, how much this power can be. These are open questions under investigation with Anne in particular and some other guys about whether whether you reach or not some unitarity bounds or something like this. So it's but it will be like in a local case. One of the possibility, you just can arrange such that this f of box will go to essentially to 1 at infinity. There is no prohibition for this. Yes, but they will not contribute to the question which you ask because your question is relevant for deep UV regime. Okay.
How many experiments were performed to fix the theory completely in terms of the three parameters?
This is a good question. How many experiments you need to? Maybe many, let's say. Okay, I will not tell you explicitly that you have to make infinite number of experiments because there is a chance that you will fix shape of this exponent somehow trickily once for a while. Okay.
Maybe we postpone this question to discussion session, and we have 10 minutes.
Okay. Well, but we'll jump to it during coffee. Yeah? Anyway, it's a good question. How many experiments you have to perform? But you know, like Planck curve for spectrum, yeah, you don't need many experiments to prove this Planck curve, yeah, even though it has some exponential shape. It's fixed by one parameter in the exponent. Okay. I mean, standard Planck curve for spectrum of the black body. Yeah, it has exponent, but you don't need infinite number of experiments to fix all of it. You just guess that it is exponent, and then you fix one coefficient in it. Okay. So it's not like a unique story in physics that you have something explained by exponent and have to fix all the possible Taylor coefficients in it. Yeah, you have to just to guess which kind of exponent it can be, and then in principle you can try to do it. Okay. Yeah. 10 minutes. Yeah. Okay. Good. So even though, as I told you, even though I was actually happy when we came to all these results here or there and also embedded here inflation, because it looks like unitary and renormalizable. The question was what happens with the singularity. Okay. Or better to say, my expectation was that we should have no singularity in this particular action. Okay. Or to put it more rigorously, I was expecting that singular solutions like Schwarzschild, for example, or Kerr, or whatever you know, and like to have in universe, the singular solution don't pass through equations of motion. However, I don't say that we have no black hole, okay? I don't say that we have no something looking like a black hole. And from far away, it should be a black hole, because as I told you, there is a scale. This scale is large. Well, it was large, yeah? So it is large scale, yeah? This inflation, yeah? This is inflation. So it is large scale. It is telling us that these effects come in force only when energies are very high. So when we are far away, we should live in GR. Yes, in GR, from GR perspective, from far away, we should see something looking like a black hole. But now we are going inside of a black hole, and we want to understand what happens when we approach singularity, or what would be singularity. And to study this particular question of singularity, I have selected black holes just because studying cosmological singularity looked like much more involved computation. Now, when I speak about black holes, I mean, we wanted just to ask the following question. Suppose we have a metric, and this metric looks like this. Let me. This is standard Schwarzschild metric, yeah, in static coordinates. And here m is mass of the object. And the question was very simple. The question was, I started with this metric just because it's the simplest one which I could start with. Moreover, it produces fantastic R mu equals 0, yeah, in 4 dimensions. So my question was very simple. My question was, what happens if I just try to plug this metric inside of equations of motion? Yeah. The problem is, however, that equations of motion are very complicated, and I cannot plug it there easily. One of the complications is, and you give me only 5 minutes for this, yeah? One of the complications that I had to study some object which is looking like this. For example, okay? Which is, yeah, and here it would be summation over n. Object like this is just some example term in my equations of motion, which implies infinite number of derivatives acting on scalar curvature. Of course, I know how to perform infinite number of derivatives acting on a function, but the problem is that if you compute R, scalar curvature, in Schwarzschild metric, R is a brilliant example because R is an invariant, yes? R is so it doesn't change with coordinates. If you compute R, it's always 0 apart from one point, which is 0, because at 0 we cannot define it. Now, what we learned from standard book on GR, we learned that we simply take our manifold, which is a big one, we have the 0, and we exclude this point, okay? We simply exclude it and say, okay, there is no this point, let's consider without it. It's a brilliant consideration, but here I have to still discuss what does this mean. And because he gives me only 5 minutes, I cannot discuss this in all details, but you know that we cannot define infinite, we hardly can define action of derivative in a point where function is not defined, okay? Neither you can exclude a point, because you have to solve a boundary value problem because you have infinite number of derivatives. And we have infinite number of derivatives because I convinced you, or at least I tried to convince you, or at least I convinced myself that I need infinite number of derivatives. And because I need infinite number of derivatives, I cannot anymore exclude this point. So unfortunately, it is my point, okay? It is my very genuine point in the manifold, R equals 0. And I have to speak about this point, and I have to say what to do with this point, and I have to consider it. What I do differently. It was our recent paper with Anna, which we wrote about black hole singularity. We did different way. We put here some function which would supposed to regularize this metric, like this. And we put here this function. It's a bit tricky function, which is in the exponent of inverse radius. We did it by purpose because our intention was to regularize all possible contributions to equation of motion, including all possible infinite derivatives. With this contribution, what we did, with this substitution, with this regularization function, what we did, which does the job, which does all the contributions regular, what we found that we, of course, cannot compute like, what is the right-hand side of equation of motion. It's a bit difficult, yeah? But what we can do, we can take these equations of motion and we can take a trace, okay? And when we get a trace, we can perform integration from 0 to infinity over radius. Why do we do it? We do it for two simple reasons. First of all, trace is still a scalar invariant, so it should not change upon coordinate change. And we do this integration because this integration should reveal me the total energy of my object, which is mass, okay? This is apparently an operation which I can do explicitly and analytically in this for this hugely complicated equations with this particular regularized function for Schwarzschild geometry. Why do I like either this regularization? Okay, maybe this is not relevant. I like it because, okay, so this will be for discussion session. But what the next step here, when I do this computation with this particular regularization, what I find out in all this computation, I find out upon these integrations, I found out some contributions. One of them is just M, which comes from GR term. And another is some summation, which includes some coefficients. And these coefficients, which we compute, are represented by our geometry. Yeah? And this Fn is coming from the expansion of our form factors. Okay. And so now my trouble is if I can ever make this summation to be at least finite, okay? And better to say, I would be happy to have this summation equal to M, okay? So this was a task which we performed. And this task is fairly well motivated because if you just do this kind of trick in jar, you will explicitly reveal that this integration gives you mass for a Schwarzschild metric. It's a very simple computation which you can do. But if you do this computation in a more general theory, you will find out something very complicated. Yeah, something much more very complicated. It's a bit strange, but we could make it analytically. Or better to say like this: we brought it to such integrals where every of them could be performed not numerically in Mathematica, even though we don't know complete finite analytic answer for all the expressions, we could analyze it computing analytically all the integrals for some orders from 0 to something, and then find out that what we have is the following. We have now the following picture. We have one of the things is alpha going to 0, this parameter which restores you Schwarzschild solution, okay? And another thing we have here, let's what we name total energy, okay? And what we found out a very simple thing, which we liked very much, and we named it like we put a statement like quantum gravity denounces singular black holes, because what we found that when alpha goes to 0, the total energy which we identify with this particular procedure of computation is going to infinity. And this is true as long as we assume that our Fn coefficients here are such that propagator still corresponds to the situation when theory is renormalizable, or better to say that it is growing enough, faster enough to have some extra suppression, like this exponent of omega, at least goes to as chi squared, such that you have suppression which gives you 1 over chi to the fourth propagator, and as such you get a renormalizable theory. So from here we make a conclusion, which is, yeah, by the way, if you want Schwarzschild black hole, okay, fine, you can make it here, and you can make it singular. You can make things like that when alpha goes to 0, this energy is still finite. Okay, you can do it. You can embed here singular black holes, it's okay. But the price which you will pay the price that corresponding propagator will not give you renormalizable theory. Okay, so here we make we have to make a choice, and we are much more fascinated to make a choice that we don't have singularity. Actually, it was an expectation, yeah? Because as long as you say theory is renormalizable, it means that it should behave well at high energies, which is small distances. So why should it have singularity at all, yeah? From here, it doesn't exclude that you have an object with a horizon. You can have a horizon here, as well as you can have inner horizon here. What's the problem? There is no problem, actually. There is only computational problem. We don't know how to construct such a solution explicitly and describe its matter content. But we are hopeful that we will be able to do it in some near future. And it looks like I have to stop, so I'm stopping here. Thank you very much. And I'm happy to answer your questions.
We had already questions during the talk, so we postponed the rest of the questions to the discussion session after the coffee break. We will meet at 11:35. Let's thank all the speakers of the morning, Alexey and Damiano.